Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin. His moral philosophy offered a naturalistic account of ethics, grounding morality in human sentiments and social conventions. His critique of religion questioned the rational basis of religious belief, prompting a re-evaluation of the relationship between faith and reason. Hume's influence on subsequent philosophical thought is undeniable. His empiricism inspired generations of philosophers and scientists, shaping the development of logical positivism, pragmatism, and other influential movements. His skepticism forced philosophers to confront the problem of induction and the limits of human knowledge, leading to new approaches to epistemology and metaphysics. His moral philosophy influenced utilitarianism, emotivism, and other ethical theories, shaping contemporary debates about morality and justice. His critique of religion contributed to the rise of secularism and atheism, and it continues to inform discussions about the role of religion in modern society. The modern legacy of Hume's skepticism is profound and multifaceted. It serves as a constant reminder of the importance of critical thinking, intellectual humility, and the need for rigorous evidence in all areas of inquiry. It encourages us to question our assumptions, to challenge conventional wisdom, and to be open to alternative perspectives. It promotes a spirit of intellectual curiosity and a commitment to the pursuit of truth, regardless of where it may lead. Hume's skepticism is particularly relevant in our contemporary world, where we are constantly bombarded with information and misinformation. It provides us with a valuable set of tools for evaluating claims, identifying biases, and distinguishing between evidence-based reasoning and unsubstantiated assertions. It helps us to navigate the complexities of modern life with greater clarity and discernment. Furthermore, Hume's emphasis on the role of emotion in human life has important implications for our understanding of ethics, politics, and social relations. It reminds us that reason alone is insufficient to guide our actions, and that our emotions play a crucial role in shaping our values, our beliefs, and our behavior. It suggests that a truly rational society must take into account the emotional needs and desires of its citizens. In conclusion, David Hume was a towering figure in the history of philosophy, whose ideas continue to resonate with us today. His empiricism, his skepticism, his moral philosophy, and his critique of religion have profoundly shaped our understanding of knowledge, reality, morality, and the human condition. His legacy is a testament to the power of reason, the importance of experience, and the enduring relevance of philosophical inquiry. He left behind a world far more aware of its own limitations, and therefore perhaps more capable of wisdom. Stirling's initial major contribution to the field offers a compelling glimpse into his intellectual prowess and his dedication to resolving the computational challenges of the day. His work, published as Linea Tertiodinea Jordinius Newtonius, was not a mere commentary on Newton's classification of cubic curves, but a profound expansion and refinement of it. Newton, in his groundbreaking work, had laid the groundwork for understanding curves beyond the simple conics, the circles, ellipses, parabolas, and hyperbolas familiar from classical geometry. However, a systematic and comprehensive understanding of curves of higher order, particularly cubics, remained elusive. The problem was the lack of a unified and readily applicable methodology for analyzing their properties. Stirling's approach was characterized by a remarkable combination of rigor and elegance. He tackled the problem head-on, providing a detailed and systematic analysis of Newton's classification scheme. He not only clarified ambiguities and filled gaps in Newton's original presentation, but he also significantly extended the classification, offering new insights and developing more efficient methods for analyzing these complex geometrical forms. This achievement reflects his deep understanding of analytic geometry, the application of algebraic methods to the study of geometric shapes. The work demonstrated his exceptional mastery of the existing tools of calculus, while simultaneously hinting at his future talent for developing new and more powerful techniques for handling complex mathematical series. He meticulously examined the various types of cubic curves, organizing them into families and subgroups based on their properties, and thereby bringing a much-needed order and clarity to this previously chaotic field. His work was a testament to his ability to synthesize existing knowledge and to his capacity for making significant advancements within a well-established framework. The Lineae Tertiodinis Newtoniae is more than a historical artifact. It is a testament to Stirling's early brilliance. It showcases his capacity to not only master existing mathematical frameworks, but also to identify their limitations and to push the boundaries of knowledge through rigorous analysis and elegant solutions. The work's lasting impact lies in its demonstration of Stirling's profound grasp of analytic geometry and his skill in managing the complex calculations inherent in the study of higher-order curves. This early success foreshadowed the remarkable contributions he would make in the years to come, contributions that would fundamentally reshape the landscape of mathematical analysis and significantly improve the computational power of calculus. The precision and elegance of his approach, even in this early work, provided a clear indication of the intellectual force that would soon revolutionize the handling of infinite series. His ability to organize and systematize a previously unwieldy body of knowledge was a powerful prelude to his later achievements in the realm of series summation and interpolation. The seeds of his future breakthroughs were clearly sown in this early and impressive contribution. The elegance of his treatment of cubic curves, a testament to his mathematical prowess, would soon be matched by the power of his methods for taming the complexities of infinite series. The early promise displayed in Stirling's work on lines of the third order culminated in his magnum opus, Methodus Differentialis, Sive Tractatus de Summation e Interpolation Seriarum Infinitorums, published in 1730. This treatise, a landmark achievement in the history of mathematics, tackled a critical challenge of the era, the effective manipulation and calculation of infinite series. These series, representing a gateway to solving problems in diverse fields from celestial mechanics to financial modeling, frequently suffered from slow convergence or outright divergence, rendering them impractical for precise computation. The world of 18th-century mathematics was awash in infinite series. Newton, Leibniz, the Bernoullis, and many others had developed methods for expressing functions as infinite sums, unlocking the potential to solve differential equations, approximate transcendental functions, and model physical phenomena with unprecedented accuracy. However, this power came with a significant caveat. Many of these series converged so slowly that calculating even a few terms provided insufficient accuracy for practical applications. Other series stubbornly refused to converge at all, presenting an apparent dead end for analytical investigation. Consider, for example, the problem of calculating the value of an annuity. The present value of a stream of future payments depends on discounting each payment by a factor that involves compound interest. When these payments extend over many years, the resulting formula becomes an infinite series. Similarly, in astronomy, calculating the position of a planet required solving differential equations that often yielded solutions in the form of infinite series. The practical astronomer needed to compute these series to a high degree of precision to make accurate predictions, a task often stymied by slow convergence. Stirling's Methodist differentialists offered a suite of innovative techniques designed to accelerate the convergence of slowly converging series and to extract meaningful information from divergent ones. His approach was rooted in the calculus of finite differences, a field that studies the relationships between the values of a function at discrete intervals. By cleverly manipulating these differences, Stirling developed methods for transforming slowly converging series into rapidly converging ones, significantly reducing the computational effort required to achieve a desired level of accuracy. A central theme of Methodist differentialists is the art of interpolation, the process of estimating the value of a function between known data points. Stirling recognized that interpolation was intimately connected to the summation of series. If one could find a continuous function that closely approximated the terms of a series, then the integral of that function could provide a good estimate of the sum of the series. This insight led him to develop powerful interpolation formulas that could be used to approximate the sums of a wide variety of series. One of the most remarkable aspects of Stirling's work is his systematic development of what are now known as Stirling numbers of the first and second kind. These numbers arise naturally in the context of converting between falling factorials and ordinary powers. A falling factorial, denoted x to the power of n in parentheses, is defined as x times x minus 1 times x minus 2, and so on, down to x minus n plus 1. Stirling recognized that any power of x could be expressed as a linear combination of falling factorials, and vice versa. The coefficients in these linear combinations are the Stirling numbers. Stirling numbers of the first kind, often denoted x of n k, count the number of ways to arrange n objects into k cycles. A cycle is a permutation in which each element maps to the next, eventually returning to the starting element. For example, the permutation 1 goes to 2, 2 goes to 3, and 3 goes to 1 is a cycle of length 3. Stirling numbers of the first kind appear when expanding x to the nth power in terms of falling factorials. Stirling numbers of the second kind, typically written Z of n k, enumerate the number of ways to partition a set of n objects into k non-empty subsets. Imagine distributing n distinct balls into k identical boxes, ensuring that each box contains at least one ball. The number of ways to do this is given by the Stirling number of the second kind. These numbers arise when expressing a falling factorial as a linear combination of ordinary powers. The significance of Stirling numbers extends far beyond their initial appearance in Methodist differentialists. They have found applications in combinatorics, probability theory, numerical analysis, and various other branches of mathematics. They provide a powerful tool for counting and classifying combinatorial objects, and they play a crucial role in the analysis of algorithms and the approximation of functions. Consider the problem of approximating the sum of the series 1 squared plus 2 squared plus 3 squared, and so on, up to n squared. This is a relatively simple series, and a closed-form expression for its sum is well known. However, Stirling's methods provide a powerful way to derive this result, using the calculus of finite differences. One can express the sum on k squared as a linear combination of falling factorials, specifically k times k minus 1 plus k. The sum of a falling factorial is easily computed using a simple formula, and the sum of k is also straightforward. Combining these results, one obtains the familiar formula for the sum of the first n squares, n times n plus 1 times 2n plus 1, all divided by 6. Stirling's Methodist differentialists is replete with examples of this kind, demonstrating the power and versatility of his techniques. He applied his methods to a wide range of series, including those arising in the calculation of logarithms, trigonometric functions, and other important mathematical quantities. He provided detailed tables of Stirling numbers and other useful coefficients, making his results readily accessible to other mathematicians and scientists. The impact of Methodus Differentialis on the development of mathematics was profound. It provided mathematicians with a powerful arsenal of tools for tackling the challenges posed by infinite series. His methods for accelerating convergence and interpolating functions greatly expanded the range of problems that could be solved with precision. The introduction of Stirling numbers provided a new framework for understanding combinatorial structures and laid the foundation for future developments in combinatorics and related fields. The work served as a vital bridge connecting the theoretical world of infinite series with the practical needs of astronomers, physicists, and actuaries, providing them with computationally tractable methods for solving real-world problems. The exploration of infinite series within Methodus Differentialis was a rich and multifaceted achievement, but it represents only one facet of Stirling's enduring contribution to mathematics. His name is perhaps most indelibly linked to a formula that transcends the confines of pure analysis, reaching into the heart of probability theory and statistical mechanics. Stirling's approximation for the factorial function. The problem this approximation addresses is deceptively simple to state, yet profoundly impactful in its implications. The factorial of a positive integer, denoted by n factorial, represents the product of all positive integers less than or equal to n. For small values of n, the factorial can be computed directly without undue effort. However, as n grows, the factorial explodes in magnitude with astonishing rapidity. Calculating 30 factorial, for instance, requires multiplying 30 integers together, a task readily handled by a modern computer, but computationally prohibitive in the era before electronic calculators. For values of n in the hundreds or thousands, direct computation becomes utterly infeasible, even with the most sophisticated manual techniques. This computational barrier posed a significant obstacle to progress in several areas of scientific inquiry, most notably in the burgeoning field of probability theory. Consider, for example, the binomial distribution, which describes the probability of obtaining a certain number of successes in a sequence of independent trials, each with a fixed probability of success. Calculating binomial probabilities often involves evaluating expressions containing large factorials. Abraham de Moivre, a contemporary of Stirling, grappled extensively with this challenge in his work on probability. He sought a way to approximate these factorials, thereby circumventing the computational bottleneck and unlocking new insights into the behavior of probabilities for large numbers of trials. De Moivre successfully found the general form of the approximation, recognizing that n factorial could be approximated by a continuous function involving powers of n and the exponential constant e. However, his formula was incomplete. It lacked a crucial constant factor, an omission that prevented it from being a precise and reliable tool. The determination of this constant factor proved to be a significant hurdle. Stirling's unique solution lay in his ability to identify this missing piece as the square root of 2 pi. This seemingly innocuous constant, deeply connected to the geometry of circles and the properties of the normal distribution, completed the approximation and transformed it into a powerful analytical instrument. Stirling's approximation, expressed as n factorial, is approximately equal to the square root of 2 pi, n multiplied by n divided by e to the power of n, provided mathematicians and scientists with a remarkably accurate way to estimate factorials for large values of n. The significance of Stirling's contribution extends far beyond a mere computational convenience. It represents a profound link between discrete mathematics, as embodied by the factorial function, and continuous mathematics, as represented by the square root function, pi, and the exponential function. This connection paved the way for a deeper understanding of the relationship between probability and analysis, enabling the development of new statistical methods and the exploration of complex probabilistic phenomena. The modern relevance of Stirling's approximation is pervasive, permeating diverse fields of science and engineering. In statistical mechanics, for example, the approximation plays a vital role in calculating the number of microstates corresponding to a given macrostate of a system. This calculation, which often involves evaluating factorials of enormous numbers of particles, is essential for determining the entropy and other thermodynamic properties of the system. Without Stirling's approximation, many of the fundamental results of statistical mechanics would be inaccessible. In computer science, Stirling's approximation finds application in the analysis of algorithms. Many algorithms, particularly those involving sorting or searching, have time complexities that depend on the factorial function. By using Stirling's approximation, computer scientists can estimate the running time of these algorithms for large input sizes, allowing them to compare their efficiency and optimize their performance. The approximation is also invaluable in information theory, where it is used to estimate the number of possible messages of a given length, a quantity that is crucial for understanding the limits of data compression and transmission. Furthermore, Stirling's approximation forms a cornerstone of modern probability theory and statistics. It is used extensively in deriving asymptotic results, such as the central limit theorem, which describes the convergence of sums of independent random variables to a normal distribution. The approximation also plays a key role in Bayesian statistics, where it is used to approximate posterior distributions and calculate Bayes factors. Its influence extends to fields as diverse as econometrics, signal processing, and machine learning, where it is used to model complex systems and make predictions based on data. The enduring legacy of Stirling's approximation lies not only in its practical utility, but also in its conceptual depth. It exemplifies the power of mathematical approximation as a tool for simplifying complex problems and uncovering hidden relationships. By bridging the gap between discrete and continuous mathematics, it has enriched our understanding of both domains and enabled the development of new theoretical frameworks. The formula stands as a testament to Stirling's ingenuity and his profound impact on the scientific landscape. Its influence continues to be felt across a wide spectrum of disciplines, solidifying its place as one of the most important and widely used approximations in mathematics. The formula's elegance and power continue to inspire mathematicians and scientists to this day, a lasting tribute to the intellectual prowess of James Stirling. The theoretical world of infinite series and asymptotic expansions formed only one facet of James Stirling's intellectual life. After 1735, a significant shift occurred, one that might seem unexpected given his prior trajectory. He returned to Scotland to assume the role of manager at the Leadhills Mining Company, a venture that would occupy him for the remainder of his career. This transition, however, reveals a deeper dimension to Stirling's character and illuminates a crucial aspect of the Scottish Enlightenment itself: the commitment to applying abstract knowledge to tangible problems. Leadhills, nestled in the Lowther Hills, was a centre for lead mining, an industry of considerable economic importance to Scotland. The mines, however, faced numerous challenges, ranging from inefficient extraction methods to the ever-present threat of flooding. Stirling's appointment signaled a deliberate attempt to bring scientific rigor and organizational expertise to bear on these practical concerns. He was tasked with improving the mine's productivity, streamlining their operations and implementing innovative solutions to long-standing engineering difficulties. Stirling's mathematical prowess proved invaluable in addressing these challenges. He applied his understanding of mechanics and hydraulics to design more efficient pumps for dewatering the mines, a critical issue that directly impacted the miners' ability to access and extract ore. He implemented surveying techniques refined through his earlier studies to map the underground workings accurately, enabling better planning and resource management. Furthermore, he brought a systematic approach to the overall organization of the mining operations, optimizing workflows and improving the coordination of different tasks. The problems at Lead Hills were multifaceted, demanding a broad range of skills. Ventilation was a persistent concern, impacting the health and safety of the miners. Stirling tackled this by applying principles of fluid dynamics to improve airflow within the mine shafts. He also addressed the issue of ore transportation, devising more efficient methods for moving materials from the mine face to the surface. His solutions were often ingenious, blending theoretical knowledge with practical ingenuity to create tangible improvements in the mining process. Beyond the technical aspects, Stirling also demonstrated a keen understanding of the human element involved in managing a large-scale industrial operation. He implemented measures to improve the working conditions for the miners, recognizing that their well-being was directly linked to their productivity. He also fostered a culture of innovation, encouraging his workforce to contribute their own ideas and insights to the problem-solving process. This collaborative approach reflected the spirit of the Scottish Enlightenment, which emphasized the importance of practical knowledge and the value of individual initiative. Stirling's work at Lead Hills was not merely a departure from his earlier mathematical pursuits. Instead, it represented a culmination of his intellectual development. His ability to translate abstract theories into concrete solutions demonstrated the power of mathematics as a tool for addressing real-world problems. He exemplified the ideal of the scientifically informed manager, capable of applying rigorous analysis to optimize industrial processes and improve the lives of those involved. The impact of Stirling's work at Lead Hills extended beyond the immediate confines of the mining company. His innovations in engineering and management contributed to the broader development of Scottish industry during the 18th century. He became a respected figure in the Scottish scientific community, consulted on various projects related to infrastructure development and resource management. His expertise was sought after in areas such as canal construction and land drainage, reflecting the growing recognition of the value of scientific knowledge in driving economic progress. The Lead Hills Mining Company, under Stirling's leadership, became a model for other industrial enterprises in Scotland. His emphasis on efficiency, innovation, and worker well-being helped to establish best practices that were widely adopted throughout the country. He demonstrated that scientific principles could be applied to improve the productivity and sustainability of industrial operations, contributing to the rise of Scotland as a major economic power during the Industrial Revolution. Stirling's contributions to Lead Hills offer a valuable insight into the practical application of mathematical principles during a period of significant industrial advancement. His career exemplifies the transition from theoretical mathematics to applied science, a shift that was central to the intellectual and economic transformation of the 18th century. He demonstrated that mathematical knowledge was not confined to the realm of abstract thought, but could be a powerful tool for solving tangible problems and improving the lives of ordinary people. The significance of Stirling's work extends beyond the specific context of the Lead Hills Mining Company. His approach to problem-solving, characterized by a combination of theoretical rigor and practical ingenuity, remains relevant to this day. His emphasis on efficiency, innovation, and worker well-being continues to be a guiding principle for modern industrial management.
He represents a bridge between the world of pure mathematics and the world of applied science, demonstrating the enduring value of both in driving progress and improving the human condition. Ultimately, James Stirling's legacy resides not solely in a collection of formulas or mathematical theorems. Instead, it embodies a powerful intellectual ethos that defined the Scottish Enlightenment, a profound belief that rigorous abstract mathematical thought attains its highest purpose when employed to address tangible practical challenges. His life's work seamlessly connects the pure mathematics of figures like Newton with the applied science that would subsequently fuel the Industrial Revolution. This connection solidifies his position as a pivotal, if often underestimated, figure in the history of science, showcasing the transformative potential of blending intellectual rigor with practical application. His career serves as an enduring example of how mathematical thinking can shape the world around us, improving efficiency, driving innovation, and ultimately contributing to the betterment of society.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.